we will welcome our next speaker, who is Julien LUMEAU. So Julien LUMEAU is a research director at CNRS. He works at Institut Fresnel, and where he's vice director and also the head of the thin film research group after a career in Aix-Marseille, in Central Florida, and so on.
Okay, there we go. So good afternoon, everyone. Thanks for the introduction and thanks for having me here to give this talk about structural colors obtained with metallic thin coatings. So this is work that has been done at French Institute, and it was partially funded by the Statue Desk. So I will start with very basic information about the nature of color. So when we talk of color, we can see that it's not something which is so simple. There were already a lot of talks about that, but I would like just to come back about how it's working. So if you talk about color, you need to pick an illuminant. So this is the light source that will shine on your object. And then this object, when it receives all these different spectral components, it will reflects or scatters part of the light, and depending on the color, we'll have more or less light depending on the spectral components. And then when it comes to your eye is not a spectral photometer where you will actually make a discrete collection of three different wavelengths, but you have actually three cones, one blue, one red, and one green. And then these three cones will process the information, bring this information to your brain, and then your brain is processing the information to say that this is red. Therefore, you can have different ways of generating colors. And this is, for example, an example of yellow colors. So one is the sodium ray or the lamp made of sodium. And you see that you will have nice yellow color. And you can get very more or less the same color with the lamp. And what's the difference between these two yellow colors? In one case, if you look at the spectrum, you can see that this light will emit a single wavelength, while for the lemon, you see that you will have the reflection of a broad range of wavelengths. And therefore, you have different ways of generating the same color, and this is what makes it complicated. So if you want to characterize a color, as we saw this morning with the speaker from Hermes, you have different coordinates. And what we decided is to go to the color coordinates, which are the most natural, as we did for the human eye, and that's the best way to understand the color. So you have the HCl coordinates. So these HCl coordinates, the H stands for hue. So the hue is what you call the color, but it's not enough. So you need to define what's the chroma. So the chroma is actually how pure is your color. And you need also to define the luminance. And you see that if you have an object that reflects just one wavelength and you set a broad spectrum, you will have a very dark color, while if you reflect a larger spectrum, you will have a brighter color. So here I'm just illustrating, for example, the same hue. So this is a red. And I actually plotted different chroma. So this is increasing chroma. So this is pure, how pure is your color. And you see that while everybody sees that this is red, you see that it can be very different. And generally what we call the best color from the point of view of human eye, this is the one with the highest chroma. So this is actually what we try to achieve. And how you can achieve this highest chroma, this is actually by generating a spectrum where you will not have any light coming to your eye in the spectral range where you don't want to have this color, the spectral components, and by maximizing the spectral components or the intensity of the spectral components where you want to have this the light coming to your eye. And that's how you get the best red. So what we question is how we can generate this color artificially. So you see that in nature, if you look, for example, like this pencil, you can generate colors with pigments. As we saw also in the first talk this afternoon, you can generate pigments by making nanostructures. But what we investigated in my team is actually how we can generate colors using thin films, so very thin layers. And the best example of color generation with thin films is the soap bubble. You see that this is a very thin film of soap and water, and you have interferences, and depending on the thickness, you can generate different colors. So we said how we can control these colors using films. So this is the outline of my talk. So I will first talk about how we can generate and control interferences with dielectric and metallic layers. Then after I will show how we can characterize precisely these metallic layers. And then after I will talk about producing colors with mixing dielectric and metallic layers. So let's consider a substrate here, which is a glass substrate, and on top of which I have deposited a very thin layer of a material that has a different refractive index. Now I will shine some light on this layer, and what will happen is that due to the Fresnel reflection, I will have part of the light that will be reflected, but generally this reflection is quite small. Therefore, most of the light enters the layer and then is transmitted. But again, you have an interface, so you can actually trap part of the light inside this layer and generate multiple transmitted beams and multiple reflected beams. And when you do that, and when you sum all these beams, we can control the reflectance and the transmittance, and you can generate interferences inside your layer. So how does it work? So if I consider a substrate with an index of 1.5, a layer with a refractive index of 2.3, and I suppose that my layer is 300 nanometers thick, I plotted here the evolution of the reflectance as a function of wavelength. And what you can see is that due to the interferences that are produced in the layer, I will be able to either maximize or minimize this reflectance. And you see that way, as we saw again in one of the previous talks, you can actually generate nice green by maximize reflectance in the green and minimize in the red and in the blue. So how can I control this color or this hue? So what I did is I consider again a substrate with an index of 1.5, the same layer, but then after I vary the thickness of my layer. And so if I change the thickness of my layer, you see that I will be able to control the number of oscillations that I would have in my spectrum. So for example, with the 100 nanometer thick layers, you see that I get the nice orange color because I'm reflecting most of the yellow and red light. If I go to 300 nanometers, I get back my green color. Then after, if I further increase, you see that I will increase the number of oscillations and I can change the color. So by changing the thickness of this dielectric layer, I can change the color. That's why it's really important. Then now, let's see how we can change other parameters, not the thickness. So actually what I did is I kept the product of the index and the thickness constant. So it's for the optical thickness. And I mostly change here the refractive index. And so if I'm doing that, what you can see that if I start with the index of 2, I will have some oscillations and I get green color. If I increase the index of my layer, I'm actually increasing the amplitude of these oscillations. And there, I'm even further increasing the amplitude. So by keeping the optical thickness constant and changing the refractive index, what you can barely see here on the screen, but trust me, this is true. Actually, I'm increasing this reflective peak, so I'm increasing the chroma. So I can do more and more pure color. Okay. But still, you see that they are not very bright because the chroma is quite small. So when you have such a layer, so I'm coming back to your to my first scheme, you see that I told you that at each interface, I'm having some reflectance with the contrast of refractive index in this boundary. So this is the classical Fresnel equations, or Fresnel reflection equation. And this reflectance depends on the contrast between the surrounding medium and the medium of the surrounding refractive index and the index of the layer. So I'm limited, or if I want to increase reflectance, I need to increase reflection coefficient of the layer. And then after, the reflection coefficient can be given by the Airy formula. I will not go further. So if I want to increase in this formula, I want to increase the maximum reflectance. What I need to do is to increase reflectance at the boundary here in between. So how can I achieve this? Is by actually adding some metallic layers. So let's see now how the reflectance of metallic layer is working. So now I move back not to a dielectric layer, but to a metallic layer. So what will happen is that in this case, the refractive index is not only a real part, but we'll have an imaginary part. And due to the fact that you have an imaginary part, you will have actually some attenuation of the light inside the layer. And therefore, we will no longer be able to have interferences. So how does it work now? This will have a metallic layer. So I consider the first type of material that is, for example, chromium, that I will call a low reflectance metal, and we will understand why. So in this case, when you have a metal, you have a real part and an imaginary part. And you see that the values are quite close to each other. So I calculated the evolutionary reflectance as a function of wavelength for various thicknesses of my layer. And what you will see that while I'm increasing the thickness of my layer, I'm increasing the reflectance, and at some point, I'm saturating. I can no longer look high reflectance. So here with chromium, I'm limited to about 5% reflectance. And what happens from the point of view of transmittance? When I'm increasing the thickness, as you can imagine, I'm actually absorbing more and more light. Therefore, I'm decreasing the transmittance until I have no more light. So now let's consider another material, but not chromium, because here I'm not very happy because I'm limited in terms of reflectance. And let's consider silver. In the case of silver, what is very different is the fact that the real part is close to zero, while the imaginary part is very high. And so how does it affect the reflectance? So I'm still looking now at reflectance as a function of wavelength and increasing the thickness. And what you can see here is that with this metal, that's why I call it the high reflectance material, I can achieve high reflectance. And from the point of view of transmittance, I'm getting the same behavior as chromium, and therefore I'm going towards zero transmittance. So if I compare the evolution of the reflectance, the transmittance, and the absorbance, which is y minus r minus 3 as a function of the layer thickness, in case of silver, as you have seen, I'm increasing the reflectance towards 100%, while transmittance is decreasing down 0%. And what is very nice and surprising is the fact that even if I have a large extension coefficient, so losses, actually I'm not having any losses. Actually, I'm getting very low absorption. And you can even see that while I'm increasing the thickness, the absorption tends to drop. So the thicker the layer, the less the absorption. In case of chromium, you see that I'm having the same behavior, but with limited reflectance. Transmittance decrease the same way. And then why? To get to that case, if I have limited reflectance, because I had absorption high. So you see that these two metals are behaving very differently. And so metals that will have a high contrast between N and K will allow us to achieve high reflectance, while the metals that have very close N and K, they will achieve low reflectance. So what are the possible materials that we can deposit in coatings? So you have the low reflectance metals like titanium, chromium, platinum, rhodium. You can see that all of them, this is the refractive index at 600 nanometers, they have N and K, so very similar. Then after you have two special case, gold and copper. So you see that gold and copper at 600 nanometers, they have a low N and a high K. But you see that they are color. They have some color. Because when you go at lower wavelengths, they tend to go to the same behavior as bad metals. And then after for the high reflectance metals, you have aluminum and silver. Aluminum has slightly higher real parts, but a very high imaging part, so it's reflecting less, but still it's quite a good reflection. So if you take these different optical properties and you take into account dispersion, which is not something that I've done not yet, but this is what I'm doing now here. You can see the reflectance as a function of wavelengths for these various metals. So you can see that silver is the best metal for gold and infrared. Then after, if you talk about also broadband reflector, this is aluminum, which is what we find. And then after, copper and gold, we do longer wavelength, and titanium or chromium, they tend to have reflectance. So now, how to characterize these metallic layers? So this is quite complex. So I'm just coming back, for example, in the case of chromium, of the evolution of the reflectance as a function of wavelength. And now let's consider, so I will first plot for a thickness of 10 nanometers, what's the reflectance for an index, the real part of the index of 2, and the imaginary part of the equal of 3. So you see that contrary to dielectric layers, I'm not having no oscillation, but I have something that's very flat. And what's very bad is that if I'm simulating the same reflectance, but by varying the index, so you see that now the real part is equal to 3, imaginary part is equal to 2, so I invert it more, but I slightly adjusted the frequency. It's the same range. You can see that. And if I continue doing that, in that case, if I'm changing even more the real and imaginary part of the index, it's likely adjusting the index. You see that once more, actually, I'm having the same reflectance. Therefore, if I'm measuring the reflectance of the spin metallic layers, I will not find a single solution for it. Therefore, it's very tricky. So how can we overcome that difficulty? So this is by not looking at the spectral properties of a single metallic layer deposited on the glass, but we move to a slightly different configuration where we decided to measure the reflectance of a combination of the silicon wafer, the silica layer, which is quite thick, and the metallic layer. So if I explain a bit more. So when I take a silicon wafer, I will have uniform reflectance. If I'm adding a silica layer, I will generate some oscillations, interferences inside the silica layer. And then if I overcoat with a metallic layer, you see that I'm severely changing the spectrum. And that way, I'm adding some information on the solution in terms of dispersion. So just to illustrate this, for example, this is the case of the transmittance and reflectance of a very thin silver layer. It's a 1 nanometer thick silver layer. And if you look at how the spectrum is changing when this layer is deposited on glass, you see that has almost no change. While if I'm depositing the same 1 nanometer thick silver layer on my silicon plus silica, you see that the spectrum is changing. Therefore, I have not very sensitive sensor that will be affected by the dispersion properties of very thin metallic layers. And so how does it work? So if I'm measuring, for example, the spectrum of this very thin layer of silver deposited on our silicon, that's what we're doing. Actually, by looking at the average value here, I will be able to extract the K and the value, where this is only affected by parameters. If I look at the amplitude of the oscillation, they are mostly only affected by the N and the values. So real part and the part of the index. And the distance between maxima will be affected by the real part of the index. So you see I have 3 independent parameters and I have therefore I have this one. So I will go very quickly because you saw this morning about that. So when you want to model the dispersion of the metal, you have different models. So we use Drude models to simulate the metallic behavior of the film. And when the metals is not behaving as a metal in some spectral region, where we use a different model, which is called Fourier-Bloomer, but this is a model using different oscillatories to be able to take into account different absorption and bands that can arise. And so if I apply my technique to titanium, and if I compare the evolution of the real part and imaginary part, so this is the real part of the text here, this is the imaginary part, so this is the evolution of this sort of wavelength. If you look at it, you can see that it has some evolution. So when I consider the constant refractive index before, this was not right. And the second thing is that if you compare this refractive index of the thin layer and of the dark materials, you can see that they are very different. So it's very important that every time the optical coatings characterize the dispersion properties of your layers, because they can be very different from the one of the dark materials. And the second thing which is important to take into account when we talk about thin layers is the fact that while some materials like titanium, they have more or less constant real part and imaginary part for different thickness of the layers. So we see that we vary the thickness from 5 nanometers to almost 80 nanometers, and the real part and the imaginary parts are more or less the same thickness. When it comes to other materials like silver, you can see that the evolution of the real part and the imaginary part can be very different for the different thicknesses. So we varied the thickness from 11 nanometers to 15 nanometers, and you see that for very thin layers, the plasmonic nature of the layers that I will explain after a while, you can see that the real part can vary from 3 down to 4. You see that depending can be very, very different. That's the same for the extension. And why do you have this behavior? It's because depending on the thickness of the layer, you have higher growth of your single layers. And therefore, you have here some plasmonic behavior of your layer before it becomes a continuous layer. And therefore, this is why you can have this very different structures. So now it's time to go to the color part of my talk. So we question how good can be the colors that we can generate with thin layers. So we decided to develop very basic colors. We decided to see how good can be blue, how good can be the green color, how good can be the red color. So in the literature, we tend to say that the best color that you can generate, this is part of the old training paper from 100 years ago, you will generate the best color by blue color, for example, by maximizing the light which is reflected between 400 nanometers and 500 nanometers, and going to 0 is red. For the green, you maximize everything between 500 and 600 nanometers. And for the red, maximize everything above 600 nanometers. So how can we approach a simple way this reflectance spectrum? So we decided to go to a structure that I already showed you, which is what we call a fabrical structure, where you have here a metallic substrate. Then you have a dielectric layer and an additional very thin dielectric metallic layer. And that way, as we tried, what I try to do, we maximize the amount of light that can be trapped inside this cavity. And when you do that, what you can do is you can actually maximize the absorption in some spectral region, maximize the absorption in certain region and minimize in the other region. From the point of view of reflectance, it means that actually you will maximize the reflectance in some other region. Therefore, you can get your high contrast between the light which is trapped in the structure that doesn't get back to your eye and the light that will go back to your eye. So we decided to start with the highly reflective metals. So we decided to take silver. Then after we took a dielectric layer, which is silica or pentitite, want to be less angular sensitive. And the last metal layer on top is actually should be a very specific metals. And in contrary to the bottom layer here, what you can show is that if you want to have a good color, you need to have the metal with the close N and K value. And what you can use chromium or titanium and deciding to use battery. So here what I plotted is the evolution of the color of the structure, which is silver, silica, titanium, and some silica layer. And I plotted the evolution of the color that you can generate as a function of the thickness of this silica layer, which is the deep cavity, and the thickness of this very thin metallic layer of titanium. And you can see that by varying these two colors, I can actually scan a wide range of colors, and these colors are very bright. And at the end, if I pick in this graph some of the colors, some of the combination, you can what you can see here is the reflectance spectra, the simulated reflectance spectra for a blue color, for a green color, and for a red color. And you see that I'm not producing exactly these very sharp variations, but it's still getting quite close. And so from the point of view of color coordinates, how that reflects. So I plotted here the average, the color gamut, that all the colors that you can generate. So in this surrounding here, the angle is the Q angle. So this is what we R or Q. And then after, when you get away from the center, you see that the color is getting darker and darker or brighter. I don't know how to say it, more intense. This is actually increasing chroma. This line here is actually what the different colors that you can find in nature can get both this type of chroma. And you see that using our layers, we were able actually to further increase and get beyond colors. And these stars, so the dots are what we calculated, and the stars, this corresponds to the profile, which were the square profiles, the one displayed. So we fabricated these colors using electron beam definition. I see that I'm running out of time, so I will not describe the technique. But what I would like to show is the final result and what we were able to achieve. So you have actually the overlay between the measured spectra, which are in the colors, green and red color, with the simulation. And you see that they are very close. So what does it mean? It means that using the different techniques I showed you to determine the dispersion curve of our metals, we're able to accurately characterize these metals, and we are able to reproduce them very accurately. And then after it here, you have pictures of the sample that we have produced. And you see that they have very nice colors, nice hue, but also chroma, especially for this red color. Therefore, it shows that definitely using optical coatings, we can produce very nice colors. The drawback is what was discussed the first talk of the afternoon. The fact that if you look at the different colors, so this is for other colors that we have produced here, the evolution of the color as if it's not an angle. And you see that they are angle sensitive. Therefore, optical coating interferences, they do not allow to produce non-angular sensitive coatings. So now I'm coming to the conclusion. So you see that the optical coatings allow producing a wide range of colors with a wide range of parameters. You see that metallic layers, they are mandatory to achieve high chroma, but these layers, they are very complex to study and analyze. And we have proposed some first solutions or some methods to analyze them, but still it's always a problem every time you talk about metallic layers. So with that, I want to conclude just with a few pictures of objects that we have developed with some designers and artists, where we did coatings on these nice colors on so boards for the historical tank, and that was for a movie that someone is trying to make. They put these colors on wood and different types of. So you see that we can do science, but we also can do when you put these colors. And with that, I will conclude that.
Thank you very much for the nice talk. Are there any questions? We have the time for a few questions. First one.
Right, from for these colors, we change it from tens of millimeters to hundreds of millimeters. It's between, let's say, 20 and 500 nanometers. Then after, depending on the thickness, also it will affect the angular sensitivity, because if you make it thicker, your interference fringes will be sharper, and therefore you are more angular sensitive. So if you want to minimize the chromatic or the iridescence effect, you need to minimize the thickness of the layer, of the dielectric layer, and also increase the refractive index. That's what we show in the slightly more distance. But we always have this effect. Yes, you can. So if you use silicon, for example, or them nanostructure, you can also use it for this, but you will be limited first in terms of thickness of your layers. So you will not be able to generate also wide gamut. So, and then the absorption will have less light coming to your eye than the reflectors, therefore the chroma will not be supported. So as it is for everything in situation of compromise, what we tried to do here was, let's get rid of this problem of iridescence and let's see how far we can go from the point of view of chroma. Because the big question is, when you start to have a nice colors, you want to have bright colors. And one funny thing that I cannot show here is that using multi-layer dielectric stacks, so it's 100 layer, we generated a nice blue, so really the perfect one. So with a chroma of 150, something like that, compared to the one that was 70. When you look by eye, so this is really what we want to assess is what's the best chroma depending on the color, and is it worth spending time and money in trying to produce better chroma? And the answer is not.
Thank you very much.
Thank you. Maybe quite a naive question. On your slide 40, you mentioned that a lot of colors outside the black line were not achievable by nature. Can you comment on it?
So when I say nature, it's quite of pigments. So this pointer gamut, this is actually something that was produced by these guys here. And they have measured a large number of objects in nature and try to see what are the color coordinates. And that's how they came to this, I would say, empirical limits from the point of view of chroma. I'm not saying that you cannot get wings of the butterflies, probably you can get further. But if you talk in terms of pigments, this is somewhat not wrong. It's hard to get beyond this. Maybe it's not complete. So again, I'm being careful. But then after, again, if you go much further, your eye is not necessarily sensitive.
Are there any other questions? Yes.
Thank you very much for presentation. Have you ever tried to use a laser on this